On number 83, once again I did a little work on the calculator. We're given the velocity or rate at which the particle is moving, and we want to know the average value, the average velocity of the particle in that interval. So this is the average value function, right? We want the average velocity, and that's going to be 1 over b minus a to b of our velocity function, right? Well, in this particular case, our start and our stop are 0 and 3. So we plug those in as the limits, the upper and lower limits. We take the difference and put that out front, right? That's where the 1/3 is coming from. We simply take and put the integrand in as the velocity function, and we evaluate. Now I got the answer e cubed, and so this was just a control enter, right, to get this one. So after I got e cubed, as I so often do, I just pushed control enter and got the decimal approximation. And if I come to my list, A is the answer. Number 84 is talking about a pizza. It's 350 degrees when it's taken out of the oven. It's placed in a 75-degree room. The temperature of the pizza is changing at this rate. We know the rate. Okay? We don't have to mess around with Newton's cooling constants or any of these things. The 75 is a bit of a red herring here. It's not needed. All we need to do is say, geez, if this is out in the room cooling at this rate for how many minutes, how much accumulated, if you will, cooling is there in those 5 minutes. So we take that rate, which is a negative 110 e to the negative 0.4 t, and we accumulate from 0 to 5 minutes, and we take and add that to our initial temperature, what was 350. And our result is 112.217. It says to the nearest degree, so A is our answer on 84. Number 8, it says a trapezoidal sum over approximates. Now remember, with trapezoidals, if you have a look like that, that is a concave down, trapezoidals underestimate, right? And if you have the look like so, when it's concave up, and you draw trapezoids, they always overestimate. So that first statement, when it says it over approximates, we know that it's concave up. And then it says a right Riemann sum under approximates. A right Riemann sum under approximates. Well, if it's an increasing function and we're using rights, right, it's going to over approximate. If it's a decreasing function and we're using rights, it's always going to under. So it must be decreasing. Remember, with rights and lefts, we're talking about increase, decrease in terms of over approximate or under approximates. With trapezoidal, we're talking concavity, with it over approximating or under approximating. So we're looking for a sketch of a function that's concave up and decreasing. And this one is not concave up, and it's increasing, so it's not that one, and this one's increasing, and this one's increasing. We have in C something that's decreasing, but it's definitely concave down, so A must be it for number 85. On this particular one, number 86, to sort of complete it, I need to have that is, to complete my region, it's bounded by the y-axis as well as the line x equals 1, right? It's got the line x equals 1, that vertical line, and it's got the y-axis as a boundary. So it's important that we understand that our region looks like this. Now, within our region, we've got perpendicular to the x-axis cross sections that are squares. So it seems to me that each one of these distances, each one of these vertical distances, is a side of a square, and they're getting smaller as we go. And these distances are always caught between this line on the one hand, 3 on the one hand, and this curve on the other hand. So this distance is equal to the difference between 3 minus the inverse tangent of x. So if we take that side length, the typical side length, and we square it and we accumulate them between 0, our starting point, and 1, our stopping point, we'll have our answer. So here is our integrand, 3 minus the inverse tangent of x. That's a side length of a square. We're going to square it to get the area of all the squares, and then we're going to accumulate between 0 and 1. So we get an answer 6.612. And so B is the answer for number 86. On number 87, we have the first derivative, and we're asked about the x-coordinate of the inflection point. I guess my approach with this is, an inflection point occurs when the first derivative goes from increase to decrease. And so clearly this function, or excuse me, this derivative doesn't exist for negative values, right? It starts when x is 0. Its domain is 0 on upward. And so we have this kind of look between 0 and 10. It's coming from the point 0, 0, and then taking off quite quickly and then falling off almost immediately. Well, it goes from increase to decrease. Remember, this is the derivative graph. So if it goes from increase to decrease, think about the derivative of it. The derivative of it is the second derivative, and it'll change from positive to negative at this moment. So I can kind of quickly identify that. If you did want to use the calculator to get the derivative, a graph of the derivative function, you could do that, and that's what I'm showing in the second drawing here, right? This is just kind of an alternative to it. That's how the curve looks. And there's that point identified once again, that x value of 0.473. So that's it for this group.